The authors present a comprehensive study on the propagation of information in random quantum circuits, focusing on the scrambling speed of information. They prove an anti-concentration inequality for the unitary Haar measure, demonstrating that the probability of a polynomial in the entries of a random unitary falling into an epsilon range is at most a polynomial in epsilon. This inequality establishes a lower bound on the scrambling speed of a random quantum circuit, showing that every input qubit has an influence that is at least exponentially small in depth on any output qubit touched by its lightcone. The authors also develop algorithms for computing the depth of a bounded depth circuit and learning log depth circuits, providing insights into the properties of random quantum circuits and their applications in quantum computing. The authors prove a lower bound on the scrambling speed of random quantum circuits, demonstrating that at least omega, n ln sequential gates are required. This is achieved through an anti-concentration inequality for polynomials over Haar random unitary matrices, a novel contribution. The authors also review related works on concentration and anti-concentration phenomena and discuss the implications for the depth test algorithm and learning algorithms for shallow quantum circuits. Additionally, they introduce a novel algorithm for learning quantum circuits efficiently, focusing on geometrically local circuits like the brickwork architecture. The algorithm achieves polynomial time complexity in logarithmic depth, contrasting with general architectures. The authors provide detailed theorems, propositions, and lemmas supporting these claims, including an anti-concentration inequality, theorems on efficient learning, and notions of quantum state in process tomography. This work offers a significant contribution to the field of quantum computing, particularly in the areas of scrambling speed and efficient learning of quantum circuits. The research paper discusses the concept of semi-polynomials and their applications in understanding the behavior of functions. Theorem 3.1 states that for a given semi-polynomial function f, the probability of f taking values close to its expectation over a unitary matrix is bounded. This theorem is proven via induction, starting with the simplest case of a single variable. The authors also consider an alternative distribution for the variable, showing that the results hold under different probability measures. The overall goal is to provide a technical framework for understanding the concentration of measures around their means, with implications for fields such as machine learning and statistical physics. The paper further discusses the application of a technique involving induction on n to show that with high probability over the choice of U1, the expected value of f, U1, un, is not too small conditioned on the fixed U1. This involves a lemma proving that if f is a degreed semi-polynomial and U1, un, is a Haar random unit vector, then the expected value of f is also a degreed semi-polynomial in U1. The authors establish a connection between the degree of a semi-polynomial and the number of variables in the polynomial, proving that the expectation of a degreed semi-polynomial in the entries of V1, Vm is also a degreed semi-polynomial in the entries of V1, Vm1. They then apply this result to bound the probability that a function f, which is a degreed semi-polynomial in the entries of V1, Vm, is less than or equal to epsilon times its expectation. The authors move on to the proof of Theorem 1.1, involving bounding the mixing time of random quantum circuits. They use a series of lemmas and propositions, including lemma 4.1, to derive an inequality and bound the product of lambda I. The proof transitions to the proof of lemma 4.1, which involves lower bounding the ratio ρ minus ρ, with a polynomial function on Guy's entries and applying Theorem 1.6. The paper concludes by proving lemma 4.1 using these propositions and Theorem 1.6, ultimately leading to a bound on the distribution lambda k. The technical details and mathematical derivations presented are crucial for understanding the underlying mechanisms and proofs in the research paper. The research paper delves into the depth lower bound for approximate designs and the depth test for brickwork random circuits. It commences by introducing the concept of an approximate unitary design and its properties, then proceeds to prove Theorem 1.2, which establishes a depth lower bound for approximate designs. This is achieved through a series of mathematical derivations, including equations 28, 29, and 30, which demonstrate the relationship between the output probabilities and the depth of the circuit. The authors also present algorithm 1 for depth testing, which estimates the depth of a brickwork random circuit by comparing the output probabilities of two different input states. The algorithm's efficiency is based on the error tolerance epsilon and the probability difference between the two output states. Furthermore, the paper discusses the process of learning brickwork random quantum circuits, focusing on the first gate G1, 1 in the first layer. It presents algorithm 1 for estimating the depth of a brickwork circuit and algorithm 2 for learning the gate G1, 1. The process involves single qubit tomography, which is poly, 1, epsilon, efficient. The algorithms use the property that the set of qubits within the lightcone of an input qubit is strictly expanding with depth. This allows distinguishing between different depths. The learning process involves uncomputing G1, 1 by applying a 2-qubit unitary G and then applying the circuit C. The distance between two qubit gates is defined, and the learning algorithm is described. The paper also includes a lemma connecting the distance with the behavior of U over the Pauli basis, ensuring the correctness of the algorithm. The paper discusses the completeness and soundness of algorithm 2 for brickwork random quantum circuits, focusing on lemma 5.5, which states that if for every sigma 1 and sigma 2, the condition trail, U, sigma 1 circled times sigma 2, U, is less than or equal to delta holds, then circled times, U, I circled times I, is less than or equal to 20 square root delta. This lemma is crucial for proving the algorithm's completeness and soundness, as it ensures that the channel phi is almost norm-preserving and almost a unitary channel. By applying theorem 1.1 to the circuit C minus its first layer, the authors show how lemmas 5.4 and 5.5 imply the completeness and soundness of algorithm 2. The algorithm's efficiency depends on the size of the epsilon net in the state tomography process, both of which are poly, 1, epsilon. The paper concludes by stating theorem 5.6, which formalizes the algorithm's properties and guarantees its performance with high probability. The research also explores the learning of quantum circuits with continuous gate distributions, introducing the concept of a Pauli rotation and its relation to the unitary matrix U2. The authors derive inequalities, 43 to 46, that imply the existence of a matrix M such that U minus M circled times I has a bounded diamond norm. This connection between U and a matrix M with a singular value decomposition is established. The paper then addresses the challenges posed by learning errors when dealing with a discretized distribution, proposing a bypass by changing the distribution from U, 4, to a discrete 1, as formalized in definition 5.7. A lemma, lemma 5.8, is presented to demonstrate how the discrete distribution approximates the original one. This setup enables the learning of quantum circuits with polynomially smaller error, making the framework more practical. Here is a combined summary of the 4 pages. The paper presents a novel framework for learning brickwork random quantum circuits, introducing a mapping that transforms the circuit into a manageable form, enabling the use of existing algorithms. The authors prove an errorless version of a theorem, demonstrating that with oracle access to the circuit, one can learn the gates in the circuit with high probability. This proof relies on Lipschitz functions and the union bound to handle cases where the determinant of a matrix is close to 0. The concept of quantum supremacy is explored, where a quantum computer solves a problem faster than any classical computer, first demonstrated using random quantum circuits in 2019. Random quantum circuits, composed of random gates applied in a sequence, efficiently simulate complex quantum phenomena, making them instrumental in demonstrating quantum supremacy. These circuits have applications in quantum random number generation and quantum algorithms, particularly in cryptography and computational complexity theory. Unitary designs, sets of unitary operators approximating the uniform distribution over all possible unitary operators, are crucial for creating efficient quantum algorithms and are closely related to random quantum circuits. The authors analyze different types of unitary designs, including exact and approximate designs, and their applications in quantum computing. The concept of anti-concentration, where the probability distribution of measurement outcomes becomes more uniform as the circuit depth increases, is essential for demonstrating quantum supremacy, with implications for quantum algorithms and quantum information theory. The challenges of simulating quantum systems classically are discussed, highlighting the limitations of methods such as tensor networks and classical algorithms. Future directions include developing new quantum algorithms and improving classical simulation techniques, emphasizing the importance of interdisciplinary collaboration between quantum physicists, computer scientists, and mathematicians. Here is a combined summary of the content from pages 29 to 32. The authors draw upon a comprehensive set of references to establish a foundation for the study of random quantum circuits, unitary designs, and anti-concentration theorems. Notable references include Fefferman et al., Fef plus 23, Fisher et al., Fis plus 23, and Ha et al. Ha plus 23, on random quantum circuits, Haferkamp's, Hav 22, work on approximate unitary T designs, and Hangleiter and Golan's, Hg 24, study on Bell sampling from quantum circuits. The authors also cite anti-concentration theorems from Hangleiter et al., Hahn plus 1-8, and Lovett's, Love 10, elementary proof of anti-concentration of polynomials in Gaussian variables. Furthermore, they reference works on learning shallow quantum circuits, such as Huang et al. Hua plus 2-4, and Landau and Luz, LL24, study on learning quantum states prepared by shallow circuits in polynomial time. The authors then explore the application of operator spreading in random unitary circuits, drawing upon concepts from quantum computation, probability theory, and the study of black holes. They reference Nielsen and Chuang's Quantum Computation and Quantum Information, and Phys. Reverend X. articles, as well as studies on random unitaries by Schuster, Haferkamp, and Huan, and Yang and Engelhardt. The discussion delves into the connections between operator spreading, quantum information, and the dynamics of black holes, highlighting the significance of Lieb-Robinson bounds in understanding local interactions. The authors emphasize the importance of considering the complexity of learning random dynamics in these systems, involving technical terms and mathematical concepts, including equations and algorithms, to explain their purpose and significance in the context of the research.